talk here. So the title of my talk is Self-Dual Yang-Mills Amplitudes from Berends-Giele Currents. And this talk is based on these two papers with my supervisor, Kirill Krasnov. Okay, I can't move the screen, I think. Okay. So the outline of the talk. So first I will give a motivation, that is why this work is important and what are its significance. Then I will talk about a little bit about the background of the work and give a brief overview of what work has been done before and what is the basis of my work. Then I will move on to part one, where I will discuss some technicalities, for example, two spinors, the theory of self-dual Yang-Mills. And then I will present a new computation, that is the computation of box amplitude from sheets. After that, I will move to part two, where I will discuss the interpretational aspects of my calculation, and then there I will discuss the sum of integrands of the one loop amplitude. Then I will represent the box plus triangles as the sum of bubbles, and then I will present a new formula for the one loop amplitudes. I will then conclude with a summary and future directions. Okay, the main motivation of this work is the problem of quantum gravity. So we know that the quantum field theory approach to gravity fails because gravity is non-renormalizable, and pure gravity is non-renormalizable. The divergences come up first at two loops, and this leads to loss of perturbative unitarity. And the divergence term in two loops is given by this coefficient, the R-cube coefficient, which was first calculated by Garoff and Sagnotti. There is some understanding of this coefficient from the recent results of Bern, but gravity is actually throwing many puzzles and surprises, so much of this needs to be understood further. So, in spite of this failure of quantum...
Pratik.
Yes, sir.
Sorry, just a question actually. Just curious, so at one loop level, it is fine.
At one loop level, yeah, at one loop level, gravity is fine, yeah.
So what does it mean? Because I'm trying to just ask this question from the, from say other quantum field theories, for example, QCD or electroweak, where when you come across divergences, say at one loop level, you know how to renormalize them, right? And then this you can do basically at every order in perturbation theory. So in gravity, what exactly happens?
In gravity at one loop, we can do field redefinitions. We can do field redefinitions, and then the divergences can be, recaptured into the field redefinitions, and then they would be neglected. They would be absorbed. The divergences do not remain in one loop. So in gravity, what happens? The first divergence come up at two loops. But with gravity, it matter. I'm talking about pure gravity, but with gravity, it matter. The divergence does come up at one loop. So at one loop, gravity is non-renormalizable when there is matter into it. When we couple gravity to matter.
Okay. Yeah. Please continue.
Yeah. So in spite of the failure of the quantum field theory approach to gravity, there has been recent surprises and understanding in the field of scattering amplitudes over the past few decades. So, for example, there are many interesting ideas that has been placed, conceptual ideas. For example, gauge theories, the scattering amplitudes of gauge theories and gravity are seen to be related to each other via the squaring relation, gravity equal to Yang-Mills squared. And also, in the last decade, there has been recent developments in the UV divergence in quantum gravity. For example, the Bern and collaborators have shown that the divergence in the two-loop amplitude is related to the one-loop amplitude in self-dual Yang-Mills and self-dual gravity. So they used the method of unitarity cuts, and they related this two-loop amplitude to the one-loop amplitudes. Further, this has been known for a long time that the self-dual one-loop amplitudes have been conjectured to be related to quantum anomalies of the self-dual currents. This has been noted by Bardeen and Kangemi in 1996 and 1997. So then what arises is that the divergence in the two-loop amplitude is ultimately related to some kind of a quantum anomaly which has not yet been discovered, but it has been linked to this one-loop amplitudes. And that is why this is very important to understand the anomaly interpretation of the one-loop amplitudes. So the overview, this is the one-loop scattering amplitude result for gluon to gluon scattering. So I will express the notations as I move on, but this is the rational result. This is a finite result with no discontinuities. There are just poles. There are just this result is very important because this is the basis of my work. So this result was first computed by using string theory inspired method by Byrne and Kosover. And later on, this result in Yang-Mills was related to the result in QED by using supersymmetric word identities, where in the loop amplitude, the particles, the supersymmetric word identities relate the one loop amplitude for particles with different spin in the loop. For example, the gluon running in the loop is related to a fermion running in the loop. And that is why this result is also valid in QED, massless QED. Later on, this result was also conjectured by soft and collinear limit arguments, and then by recursive technology. So Malone has devised a method of recursive technology. He used a recursion relation of Berends-Giele to relate this n photon amplitude, and the result come about by this factor of UV1 by epsilon poles times epsilon. So this result is related to dimensional regularization. So this result was calculated by in-dimensional regularization. The unitarity method, relates the two-loop gravity and divergence, as I said, to the one-loop helicity amplitude. And that is why it is very important to understand the interpretation of this amplitude. Now I go into some technicalities of two spinors. So what are spinors? Spinors are fundamental representations of SU2. So there are two types, half-zero representation and zero-half representation. We call it S plus and S minus. The vector representation is given by the direct product of the two spinor representations. And for every vector index, we have a two pair of spinor indices identified by this relation, K mu equal to sigma mu m prime, K m prime, where sigma is a Pauli spin matrix. If we have a null momentum, for example, where K square equal to 0, we can split this spinorial object K m prime into Km and Km prime up to scaling, rescaling. And I will use the index notations throughout my talk. So I will give a brief overview of the index notations. What does this mean? So if I have a primed spinor Km prime, I denote it by a square bracket like this. And if I have an unprimed spinor, I denote it by an angle bracket like this. And if the indices are in the superscript, so this was when the indices were in the subscript. If the indices were in superscript, then the direction of the bracket changes. So what is a contraction? So let me introduce some more technicalities. So what is a contraction in index notations? So a 4-vector, first of all, L mu becomes spinorial object LMM prime, and this can get contracted by a primed and unprimed spinor. So here the unprimed spinor gets contracted from the left and the primed spinor gets contracted from the right, and we denote by this contraction in this way. The leveling of external momenta. So when confusion does not arise, we level the external momenta by just the number of the momenta and not by any symbol. So it's related by 1 mu. And in the two spinor notations, so this is represented by this 1 mm prime, and this is represented by a angle bracket spinor and the square bracket spinor. For example, this whole bunch of contraction is given by this form, where there is a circle in between, and this represents the contraction between the mixed spinors. Okay. So now I discuss briefly about the theory of self-dual Yang-Mills. So in self-dual Yang-Mills, what happens is that there is an action. The action is given by this B plus wedge F, where B is a Lie algebra value 2 form, and F is the usual field strength of the, if it's a curvature 2 form, it is the field strength. So B is constrained to be self-dual here. And that gives the field equations. If we vary with respect to B plus, we get the field equation F plus equal to 0, which means that the theory of one of the self-dual component of the field vanishes, and that means that it is basically anti-self-dual Yang-Mills. But when confusions do not arise, we just call it self-dual Yang-Mills. And field configurations satisfying this equation are instantons basically. And if we linearize this solution, and then they describe the negative helicity polarization vector of the gluon. If we vary with respect to A, the connection, then we get the covariant derivative of B plus equal to 0. And this represents the other polarization of the gluon. Okay, now we want to linearize this self-dual Yang-Mills theory. And we linearize it on a trivial background for the auxiliary field, and on for B plus equal to 0. And on the connection, we linearize it on a background where the connection satisfies F plus equal to 0. And we denote the perturbations by B and A. So the linearized Lagrangian is given by trace B wedge dA plus 2 trace B wedge A B wedge A. And in the Lagrangian in spinor notations, so first of all, we transform all these things into spinor notations because the entire talk will be in spinor notations. So mu goes to AMM prime, B mu nu goes to BMN epsilon M prime n prime, because B mu nu is a self-dual field. So it is just the self-dual component is there. The another component, which is BMM M prime n prime epsilon M is not there. And then the linearized Lagrangian reads like this: BDA plus 2FIJKL BAA. So we can immediately calculate the propagator and the vertex from this Lagrangian, linearized Lagrangian. There is one propagator, which is given by this form, and there is the one vertex, it's a cubic vertex, which is a BAA vertex. We can also use the equation of motion and then derive the helicity states. For example, the negative helicity polarization vector is given by this QM prime QK over QK, and the positive helicity polarization is given by KM. So Q and K, so Q is the auxiliary spinner. So the auxiliary spinner stands for the gauge freedom of the theory. So if we shift the auxiliary spinner by some amount, the amplitudes remain invariant. So in that sense, it is an auxiliary spinner. So the auxiliary spinner only enters the negative helicity polarization state. Okay. So now I talk about the box amplitude. So in the paper, this box amplitude was calculated for massless quantum electrodynamics, but this can be also be done in the self-dual Yang-Mills theory, because the Feynman rules of these two theories are similar in spinor notations. So what we do is that we first try to devise this loop integral. We first write this loop integral and then project this loop integral to external states, negative helicity states. And then it takes this particular form where it is given by a spinor bracket contraction in the numerator, and in the denominator, they are the usual propagators. So this box amplitude is logarithmically divergent, but there are no discontinuities. And the result is, we know that the result is finite, right? I mean, the result is finite. So there is no requirement for regularization, and we do the computation in 4 dimensions. Because if we do regularization, we can do dimensional regularization, but there is a problem with dimensional regularization because we're dealing with 2 component spinors, and 2 component spinors are undefined in dimensional regularization. So the method we use is to calculate this box amplitude, and we first use the spinor brackets like this 4-3 bracket, where this 4-3 from now on would indicate the momenta 4 and momenta 3, for example. So we multiply this numerator and denominator by this 4-3 and rewrite this numerator in a particular form. And then we use the spinor identities. For example, there is a spinor identity where these mixed spinors A and B, A circle B is equal to minus B circle A plus A dot B for any 2 mixed spinors. We use this spinor identity to decompose the box integral, the logarithmically divergent box integral, into 3 linearly divergent parts. And the geometric representation stands like this. So this box integral is given by this triangle integral plus some triangle-like integral. So one of the integral among this is exactly a triangle integral, and the other integrals are linearly divergent integrals. And so I just tell them they are like triangle-like. So we use a process in repetition. Therefore, we repeat this process, and we again use these linearly divergent integrals and decompose them to quadratically divergent integrals. So each of these linearly divergent integrals becomes quadratically divergent integrals. And the geometric picture again stands like this. So one triangle integral is given by the bubble integral plus bubble-like integrals. And then what we use is the method of shifts. So first of all, we note that some of these quadratically divergent integrals vanish using Lorentz invariance arguments. For example, take this integral, consider this integral. So the loop momenta dependent part of this integral is given by L mu L plus 1 nu. And in any Lorentz invariant regularization, the quadratic part of the numerator can be either proportional to 1 square eta mu nu. This vanishes because the momentum 1 is null, or it can be proportional to 1 mu 1 nu. And if it is proportional to 1 mu 1 nu, the numerator in this case is given by this factor. And this factor also vanishes because there is a spinor bracket contraction of 1, 1, which is 0. So this whole integral vanishes using Lorentz invariant arguments. There are other remaining integrals which are quadratically divergent, but which vanish after a shift of the loop momentum variable. For example, consider this quadratically divergent integral. If we shift the loop momentum to L to L minus 1 minus 2, this becomes this integral. And using the similar arguments which was given above, this integral also is the loop momentum part of this integral is proportional to L mu L nu, and this again can be proportional to either 2 square eta mu nu, which vanishes because the momentum 2 is null, or it can be proportional to 2 mu 1 nu, in this case, again, according to the previous argument, it vanishes because of the spinor bracket contraction. So what we do is to consider these shifted integrals, and we perform a calculation of the shift. So consider this two one-dimensional quadratically divergent integrals. So if the integral was convergent, then we can use the change of variables, and then the difference between these two quadratically divergent integrals would vanish, right? I mean, the difference would vanish. But because it is it is not convergent, it is divergent. We first Taylor expand this fy plus b in powers of b, and then we get a finite result of this difference. So jb minus j0 is given by this quantity, where f plus minus infinity minus f minus infinity is finite. These are finite constants. And then we replace this by a loop integral. It's the same process. It's just that we replace this by a loop integral, and then we calculate the shift of this loop integral. So we know that f of L plus b minus f of L is given by this. And f of L we argued is to be 0. So in that way, we can find f of L plus b. So after using this method of shift, we basically convert this one loop amplitude by the method of shift. We calculate this, and we evaluate it, and we get the final result like this. The salient features of this calculation is basically that no dimensional regularization is used, because, as I said, that dimensional regularization will be problematic in terms of when it is used in case of two spinors. The result comes from a divergent as well as a vanishing expression, and this is very reminiscent of the chiral anomaly calculation, where the result was also, calculated using the method of shifts, and it also comes about from a divergent as well as a vanishing expression. And further, one of the main motivations of this calculation is that this shift method can be used to extract the rational result, and this can be a possible variant of the method of generalized unitarity. So the method of generalized unitarity basically calculates the rational parts of one loop amplitudes. And here we have devised a particular method, the method of shifts, to extract the rational result. This result is completely rational, but it can be used to calculate the other rational parts of amplitudes. Okay.
Pratik?
Yes.
Yeah. So just to understand this, so in this case, since the full amplitude is finite, only these sub-diagrams, they are logarithmically divergent. Using this shift technique, somehow you have decomposed your diagrams in divergent,
linearly divergent parts and quadratically.
Yeah, right. And then somehow basically you showed that they will not contribute, and ultimately you get a finite result for the full amplitude.
So some of the integrals do not contribute, but some of the integrals contribute in the sense that after shifting the integral, the result, you can calculate the shift of the integral. So by
But then probably those, you are saying basically some of the divergent integrals, they remain, but when you combine all of them, then they cancel. Is that correct?
Well, some of the divergent integrals, remain, but when we shift the loop momentum parameter of those integrals by some amount, then they are again 0. Then they again vanish using Lorentz invariance arguments, and therefore we can compute the shift. We compute the shift between the shifted integral and the unshifted part, and that gives us the result for the shifted integral.
Okay. Fine. So just to appreciate this, like as you said, because you are using this two-component spinor technique, you want to remain in 4 dimensions. So somehow, although I don't understand fully, but somehow basically you managed to get this. But now suppose that basically in a realistic calculation, I have diagrams or an amplitude where basically you cannot remove the divergences without performing the renormalization. In those cases, how would I be actually applying this technique? Because I need to know what is the divergent piece before I can go on renormalizing the amplitude.
So we have to separate the divergent piece and the piece which is rational, right? In this case, we can use a shift method to only calculate the rational parts of the one loop amplitudes. So we have to first separate the divergent piece and the rational part, and then we can apply the method of shift to these rational parts. We have to first understand which part would be divergent, which part would be related to all these divergences, and which part would be finite. I mean, if we can extract the finite parts from those loop amplitudes, then we can apply the method of shifts to the finite parts and we can extract the rational result.
Okay. So then you are saying basically this technique would in general be applicable to extract the rational piece of
any. Well,
like,
I won't claim that it would be applicable to extract. I mean, it can extract to any loop integral, but it seems that there is a possibility that this method can be used to extract the rational parts of loop amplitudes. I mean, I'm not sure of how, I mean, to what extent it can be applied. I mean, to how which loop integrals it can be applied, but there is a possibility that it can be applied to extract the rational result.
Okay, fine. Okay, we can get back to this later. Please continue.
Yeah. Okay, so next I move on to the second part of the talk. So to do that, I digress a bit into some of the technicalities. So again, so there is a understanding of dual momentum variables. So what are dual momenta? So in a planar Feynman graph, which is color ordered, we ascribe region or dual momenta to different regions in a planar Feynman graph. So if you have an external line of momentum P separating two regions K1 and K2, then P is given by K1 minus K2. And if there are loops, then we assign the region momenta inside each of the loops. So for example, take this graph and we just label these graphs by the momenta, line momenta. We represent 1, 2, and L plus 1. This is the line momenta in this graph. Instead, we can also label this graph by using region momenta. So for example, the lines separate two regions which are extending to infinity. And these region momenta are denoted by K1 and K2. So this is motivated from the worldsheet representation of the planar of the Yang-Mills theory. So inside the loop also we can ascribe a region momenta. I have not noted it down, but it can be ascribed. So here 1 equal to K1 minus K2 and 2 equal to K2 minus K1. So what we get is that momentum conservation is automatically satisfied in terms of dual variables. So if we just change the variables from 1 to K1 minus K2 and 2 to K2 minus K1, then we can see that momentum conservation is automatically satisfied. And this can be done for any planar graph where there is a color ordering. When we do the integral of the loop momenta, the loop momentum is ambiguous to define because we can shift the loop momenta by some parameter and then we can again integrate it. I mean, right? I mean, there is an ambiguity in the definition of the loop momenta. So we can use this ambiguity to choose different loop momenta for different diagrams and to simplify the computation. So for the above diagram, we just choose the loop momenta to be L equal to Q plus K1, where Q is the region momenta in this diagram. So why L equal to Q plus K1? Because the line momenta, as I said, is the difference between two region momenta. So the line momenta is L here, and L is given by Q. I mean, Q minus K1 is equal to L. So here L equal to Q plus K1, where Q is a loop variable to be integrated over. So using this, we first of all write all the diagrams, the box, triangles, and the bubbles in terms of dual momentum variables. So the box is logarithmically divergent. So it is first decomposed into linearly and then quadratically divergent integrals. And these are rewritten in terms of dual momentum variables. The triangles are already linearly divergent. So we use the method of shifts to, again, rewrite this into quadratically divergent integrals. And then these integrals are written in terms of dual variables with particular choices of loop momenta. The bubbles are already quadratically divergent. So we just label them by using dual momentum variables. So I'm not explicitly showing the dual momentum variables here, but we label them. And then what we do is to combine all the quadratically divergent integrals and group the integrals over common denominators. So after we do that, we see that the sum of integrands is basically the sum of groups with common denominators. And we see that using the Schouten identity, which is an identity in spinors, and the momentum conservation, each of the group vanishes identically. So the geometric representation of this is that the sum of box, triangles, and bubbles vanish with a particular choices of loop momentum variable in terms of dual momentum variables. So the sum of box and triangles, which is a full amplitude, that is related to the bubble diagrams. And that is the important thing here, that the bubble diagrams are zero to begin with. But if we try to shift the loop momentum parameter by some amount, then they are not divergent. I mean, then they are not zero to begin with. That I will explain further. So what is happening is that, so for the bubble diagrams, we need to calculate the self-energy bubble first. So here in the self-energy bubble, we can see that when we consider this integral seems, by using Lorentz invariance arguments, that this integral is vanishing, because it can be proportional to P. I mean, the divergent part is proportional to L mu plus P nu. And then L is proportional to P. So this PP bracket will be vanishing because of spinor identity. And therefore, this is vanishing to begin with. But if we consider the loop momentum to be L plus S instead of L for a non-zero constant S, then this integral is not vanishing. I mean, if we can calculate the shift of the integral, and using the method of shift, this gives a finite result. So the self-energy graph is shift dependent. And why it is important? It is important for the following reason, as I will tell. So first of all, I will explain a bit about the Berends-Giele currents. So how are the bubble graphs? How are the bubble graphs built from the self-energy graph? The bubble graphs are built from the self-energy graph by gluing Berends-Giele currents. These are the self-dual currents in self-dual Yang mills. So what is the current? The current is a color-ordered sum of all tree-level diagrams with all but one leg on shell. So for example, this is the 2 current. So this current has this particular index structure. So there is a QA, QB, which are the auxiliary spinors, and there is a sum over momenta, VA prime, and then there is a scalar part of the current. So we can use the recursion relation, the Berends-Giele recursion relation, to compute the scalar part of these currents. And for example, the 2 current is given by this, but there is angle bracket spinor contraction in the denominators. So this is the 2 current. The 3 current is given by this factor. So, and there is a general expression for the N current, which is given by this, where I have not written explicitly, but there is a general form of the N current. Now, internal bubbles are basically, they are basically built from gluing 2 currents to this self-energy diagram. So we can glue these 2 currents. So these legs are basically representation of the 2 currents, and they are glued to the self-energy diagram to build the internal bubbles. The bubbles on the external legs are built by gluing the 3 current to the self-energy. So this 3 current is this blob where there is but 3 legs are coming out, and it can be glued to this self-energy diagram to build the bubbles on external legs. So after we do that, we can compute the amplitude, and then we come for the new formula for this one loop amplitude, that's all multiplicity. So what is the formula? The formula states that the amplitude is written by the gluing, all possible gluing of this currents to this self-energy bubble, and the self-energy bubble is treated as an effective propagator. So this is an effective propagator, effective connection propagator, because if we go to this slide, we can see that the self-energy bubble, the A legs are coming out from these two ends. So this is the effective connection propagator, because these A legs are the connections, and therefore these currents are glued to this effective connection propagator, and then we can use the sum of all partitions of these currents, and then we can build construct the full amplitude from it. Here, obviously, there is a region momenta playing a role here. I mean, the region momenta appeared in the formula, but we can get rid of the region momenta variables by a complicated calculation. So after we get rid of the region momenta variables through a complicated calculation, we recover this usual result of the one loop amplitude. So this is the usual result. This result is known from the 90s. But what we post is a new formula for this result in terms of the Berends-Giele currents, and this accounts for the self-dual nature of the self-dual Yang-Mills theory. So the BG current representation of the amplitude manifestly satisfies a soft limit, because the current themselves satisfies a soft limit. There is a soft limit for the currents, and the collinear limit of the semi-helicity one loop amplitudes are also satisfied in the current representation, because there is current again satisfies a collinear limit, and there is a derivation. I mean, how the current satisfies the collinear limit, but this amplitude satisfies the soft limit and the collinear limit, because the current satisfies the soft limit and the collinear limits. And the formula of the amplitude is proven by showing that it is region momenta independent, and along with it, the formula satisfies the collinear and soft limit. So as I said, the region momenta appears in the formula for the amplitude, but it can be shown that the amplitude is region momenta independent by actually by performing a calculation. It can be shown that the amplitude is region momenta independent, and then along with it, it satisfies the soft and collinear limits. So the formula is proven by this fact. So I then discuss the summary and future directions. So first of all, what we did is the semi-helicity box amplitude calculation by a method of shifts. And this is one way of extracting the rational part of loop amplitudes. And then we saw that the sum of all geometries vanish with some appropriate choice of loop momenta. Further, we saw that this box amplitude is related to bubbles because of this identity that the sum of all geometries vanish with the appropriate choice of loop momenta. And then the bubble graphs are obtained by gluing Berends-Giele currents to the self-energy. So this is very reminiscent of the fact that how axial current was glued to the triangle graphs in the chiral anomaly calculation. So this is a very similar feature in this case. So it seems that there is some anomaly of the Berends-Giele currents, and we need to interpret this anomaly, but we have not yet understood what the particular anomaly is. So what are the next questions? The next question is basically that which symmetry is anomalous and what is the corresponding word identity? We have to find the symmetry which is anomalous in this case. We do not know at this point. And further, does this hold in the case of gravity? So in gravity, what happens is that a very similar thing appears. I mean, we can construct the full amplitude, the box amplitude, the box integral, the triangle integral, then the bubble integrals in the case of gravity. But what happens is that because in gravity, there is no color ordering, we cannot ascribe region momenta variables to the choice. I mean, we cannot use the choice of region momenta variables as a shift parameter, and therefore the case of gravity is still under mystery. And finally, I mean, if it is possible to do this case in the case of gravity, is it possible to write the two-loop gravity divergence in terms of an anomaly? I mean, that would be the final thing to do, because ultimately we want to show that this two-loop gravity divergence comes out from an anomaly in the currents in the self-dual gravity and self-dual Yang mills, and therefore this will be the final thing to do. So with this, I would like to end it up. Okay, so thank you.
So thank you, Pratik, for such a nice talk, and I will request the audience to please ask your question.
Yeah, I have several questions.
Yeah.
So when you say this Berends-Giele current, so this guy, is it supposed to be? It's quantum mechanically not conserved. That's why you're looking for an anomaly.
Yeah, that's true.
But what is the classical guy? What does it mean? Is there a classical idea of where this current is coming from?
So there is a classical idea. So basically the current is basically a solution of the self-duality equations. So if we solve the self-duality equations, we can represent it as in terms of the current. So the current is a solution. I mean, that is the classical interpretation of the current.
I see.
Yeah.
But this current now has some kind of two extra Lorentz type indices, right?
This current has two Lorentz.
It is associated with.
This current has one.
It has totally three. Oh, it
Sorry?
has only two indices.
Two spinor indices, yeah.
So sorry, it has two spinor indices. So
it is a vector index.
So the two spinor indices are just one vector index. I see.
Yeah.
Okay.
Yeah.
So it is really an ordinary. I thought somehow I was under the impression that because there are these. So the choice of the helicity on the 2 minus and the 1 minus legs, can I change it to some other helicity choices?
Yeah, of course you can change it, but it will not give something interesting. I mean, the interesting part arises here. I mean, if you can always devise a current with different helicities, that is not a problem. But for this case, the recursion relation is known. I mean, for this case, when there are these two negative helicities, so we can solve the current using the recursion relations, and we can get a compact formula for the current.
So I see. I was wondering to what. So I was kind of following up on Ambresh's question about there is a technology here that you are starting with a box diagram and rewriting, let us say, the rational part of that box diagram in a certain way.
Yeah.
Right.
Yeah.
Now, so of course there is a transcendental part of that box diagram as well, right?
Yeah.
Not a non-rational part.
No, the box diagram is completely rational.
Fully rational.
Yeah.
In this case, it's fully rational.
Yeah.
You see, in an arbitrary Feynman diagram, there will be these things, right? There will be rational parts and transcendental parts. Now, so some of these transcendental parts are written in terms of some functions, like polylogarithmic functions and things like that.
Yeah.
And the the point is that if this was a way to isolate the rational parts, so is there an algorithm that I can sort of imagine devising which would help me do that?
That is not yet known to me. I mean, I have not tried to apply this method to some arbitrary Feynman graph. I mean, what I can say is that it is possible that one can extract the rational part from an arbitrary Feynman graph and then use this method to calculate the rational part. I mean, like one uses the generalized unitarity method, right? I mean, one uses the generalized unitarity method to calculate the rational parts of one loop, the loop amplitudes. So in a similar way, without using the generalized unitarity, one can use the shift method. So it is the alternative variant in that sense. Yeah, so I mean.
So another question was this. So when I say that the box diagram can be written in terms of the triangle diagram, so can I understand it? What is that recursion relation there? Yeah, what is this equation, for example?
Okay, so here I am using some identities. So I am using a spinor identity of this form. So with these spinor identities, I can cancel propagators. So I can use these spinor identities to write the numerator in a certain way, such that one of the propagators appears in the numerators and the propagator gets cancelled. And then it boils down to these integrals where there are 3 propagators instead of 4. And that is why they are linearly divergent.
I see. So, I mean, the thing is, I'm a little curious about, for example, is there a way to understand going from the box to the other figure by, let us say, star triangle transformations in resistor circuits and things like that? Or let's say, what is it called? Pinching rules or cutting rules?
By pinching rules, one can, there is a method of cuts where one uses this method of cuts to go from the box to triangles. And this has been done by Byrne and collaborators. I mean, I have seen the paper.
So is that the same as your spinor identity?
Well, that I'm not sure because I'm using a completely different route here. I mean, I'm using the method of cancelling propagators by using the spinor identities. In the cut method, I mean, I'm not sure what they're using, but there is a method like that. I mean, yeah, in the papers of Byrne. So, but I'm not sure that it is similar to the spinor identity or not. No, I'm not sure about that.
So I see. So you see, the point is that as far as kinematics is concerned, the momentum flow, the total momentum conservation applies at every vertex.
Yeah, that's true.
So we can think of this left-hand side as a resistor circuit with currents, electric currents coming in through the external legs. And then the transformation from the left to the right. So now if I want to do some Kirchhoff rules, whatever in school level electricity, no? Then I can use some star triangle transformation. The question is, is this calculation that you're doing a recursion relation of that type?
So this calculation is based on a recursion relation of the Berends-Giele type. So we are not, Malone used this recursion relation to calculate this amplitude. He calculated the general endpoint amplitude from this recursion relation, but we are using this recursion relation to calculate the 4-point amplitude. It is just reminiscent of the Malone calculation. But in the Malone calculation, what he did was he used dimensional regularization to regularize the integral and then use these recursion relations. But in our case, we are not using any regularization. That is the difference.
Okay.
Yeah.
Okay. Okay. Yeah. Thanks. Yeah.
So, any more questions?
Pratik. Yeah. So, so to understand it further, since so was there any specific reason that you are actually looking at the box only? Like what about actually pentagons and all those things?
There is a specific reason because the box amplitude is conjectured to be related to some anomaly, because I mean the 4-point amplitude, which is the box, is conjectured to be related to some anomaly in the self-dual currents. That is the main reason, that is the main motivation for looking at the box.
I see.
Yeah.
Okay.
So we want to understand what kind of anomaly it is. So it is still not known. I mean, that is the main motivation.
Okay. I mean, through your work, you have established that there is a connection between anomaly and the rational piece.
Yeah, that's true. I mean, the rational piece is calculated by the method mimicking the anomaly calculation. I mean, it mimics the anomaly calculation.
Okay.
Yeah.
Okay. And I mean, I'm not sure, but probably, I mean, at least in the example that you have taken, all the particles are massless. But you know that in general, there are generalization of spinor techniques for massive fermions.
Yeah.
Yeah.
So for for massive fermions, I mean, one can use the method of generalized unitarity, right? I mean, one can use the method of generalized unitarity to extract the rational parts of the amplitudes. But in our case, we are just concentrating on the massless particles because we are just using pure Yang-Mills. I mean, pure Yang-Mills theory, pure self-dual Yang-Mills. We are not coupling to matter. But when we couple to matter, one can use the method of generalized unitarity. So that is one thing that is there.
Okay. I mean, so are you saying basically that in presence of matter, the shift techniques would not actually work, or you haven't? Yeah.
We haven't understood the shift techniques in the presence of matter. As of now, I mean, if the structure of the loop integral is like this, I mean, it's like just denominators, I mean, and spinor bracket contractions, one can apply the shift technique by using spinor identities. So in matter, this would change, I mean, because there would be m squared here in the denominators. And then we will be not sure that whether we can cancel the denominators from the numerators. We have to cancel the denominators to apply the shift technique, and that is not sure about what if you have matter in it. So that is the problem.
Okay.
Yeah.
Okay. Yeah. Okay. Because in like, for example, in the standard model, the anomalies that we talk about, they are specifically due to the fermions, right?
Right. That is true.
Yeah.
Yeah.
Okay. Okay. Yeah. I'm fine. Thanks.
Okay.
Any more questions? Okay, if not, let's thank the speaker again. Thank you, Pratik, for nice talk. Yeah, so thanks, Pratik, and thanks everyone for joining. We'll see you guys the next time.
Okay. Thank you.
Bye-bye.